let's take a look at the digital panel voltmeter. I'm going to zoom down this because it is quite a tiny thing, although it does have fairly big digits. Can't remember the size of the digits, but it's decent. And this thing is rated apparently from 70 to 500 volts. I have to say, with a little connector like this, I'm not really sure I'd really fancy trying it at 500 volts. Although certainly you could put a small HRC fuse in line with it, a control circuit fuse. Now I'm going to grab the tester here and we shall test it. So I shall stuff the wires in and then turn it on without actually holding it at the time, because I do have a lack of trust in such things. So I'll plug this in now, put it up like this. This one incidentally is red. There are other colours available, but I chose red just because the red LEDs have the longest sort of lifespan. So that says 250 volts, don't think that's terribly accurate. Oh, there we go. Right, I'm going to carefully hold it. It's not that bad for brightness either, by the way. 245 volts. Now see the shimmer, the flicker, that is the multiplexing, and if it looks a bit odd, it's because it's using tri-state multiplex. I can tell that just by glancing at the back and seeing the pins, but to the naked eye here, it's pretty good. Let me show you what that looks like to the naked eye. One moment. And that's what it more or less looks like. I would say that the camera's still showing a slight shimmer, but I'm not seeing that at all, except when I swipe my eyes about, and then you can see the slight multiplexing just because of the way it works. Technically speaking, only one segment is lit at a time. Right, okay, tell you what, I'll bring the light back and then we'll take this apart. I'll bring the light back right now, so watch your eyes. The light is back. I've connected to the anti to get a better reading of things like the power factor and stuff. So its power rating is about 0.2, so let's say 0.3 watts. Its current is 27 milliamps and its power factor is a really low 0.04, but that's just because of the way the circuitry works. It is a capacitive dropper. Okay, right, let's unplug that and see if we can hike the circuit board out of this. So I'll put that down there, put the vice of knowledge out of the way. I was using that just to temporarily hold it. So the way these circuit boards are normally held in here is these side tangs. So I have to very carefully try and prise the circuit board out while pushing this little tang back. And that can be quite tricky at times. Some of them are very, very tight indeed, which is good in a way. It stops it being pushed in accidentally. That is not necessarily coming out too easy. Then let's try again. I shall drag on the cable while lifting this up. Oh, that's not even coming out like that. That is very tight. Oh, here we go. Here comes the circuit board. As always, we have the clear plastic front in it. I'd like to remove that. That's part of the manufacturing process, I think. They put this clear plastic film on and then pot the resin into it, and this stops it dribbling out the front. So I tend to prefer to peel that off. Not that it really matters, because there is a diffused plastic in here. So the circuit board has the dropper capacitor. It's got a smoothing capacitor, inrush limiting resistor. It's got a tiny little potentiometer here, and then the chip that's doing all the stuff in a rectifier. Okay, I'll take a picture, reverse engineer it, and we can explore it more. One moment, please. Reverse engineering is complete. Let's explore. So I shall zoom down into this circuit board a little bit. And the circuitry is powered by a capacitive dropper. That's a very simple, cheap way of doing it. There's a capacitor here that rations a small amount of current through in each half of the mains cycle, and that gets rectified and charges up this capacitor via this half-assed inrush limiting, strangely big resistor with a low value. And then there's a Zener diode which caps the voltage around about 5 volts. Under the capacitor there are two hidden resistors, 750k discharge resistor and a 2 mega ohm resistor which forms part of the potential divider over here to provide a reference voltage from the incoming supply so the chip can measure the voltage. The chip then drives the display directly with just 6 pins and tri-state multiplexing. There is a mystery resistor down here which I think might be a fuse, not sure what the function of this is, but this connector here has anti-tracking slots under it, which is good, particularly given how close the connections are together. But it also has an option for 3 positions, the supply and a signal if you want to use the meter in a different configuration. The rating of the meter is supposedly 70 to 500 volts AC. Okay, let's take a look at their schematic because it will make more sense of this. Here is the schematic. I'll come up to this bit in a moment. This is the tri-state multiplexing. So here's the AC supply coming on, and it goes to the dropper capacitor, 630 volt, 330 nanofarad, with its discharge resistor across it. It also goes across via the other resistor to the divider. But that limits the current to the bridge rectifier. There is this strangely low value spike limiting resistor here. And then there is the smoothing capacitor, and I'm guessing this is a 5.1 volt Zener diode because I measured 5.04 volts on the rail, and they tend to have very specific values, and 5.1 is the closest to that. There is a potential divider based on the 2 mega ohm resistor, and then a rather oddly specific 4.22k resistor, and then what measures in circuit as a 3k potentiometer. Not sure the exact value without taking out the circuit. That provides a divided voltage to the IC so it can measure the incoming supply voltage. There is the position for a capacitor for filtering of that, but they've not included that. At 245 volts supply voltage, I measured a range by taking this potentiometer from one end to the other. I measured a calibratable range of 174 volts to 303 volts, which is quite a high range actually. It made it very fine for tuning, but I did use a Fluke meter to check the mains voltage. It was 245 volts. I tuned it, and it took, if you move it a slight bit, you have to wait for it to average the value and then stabilize again. But I tuned it to exactly 245 volts. So it is reasonably usable in that way. Here is the IC, which is an unknown IC. I don't know if it's a dedicated meter chip, which would make sense actually. But there is the 7-segment display with 24 LEDs and just 6 lines feeding it. Let me explain the tri-state multiplexing that allows them to control that number of LEDs with just 6 lines. And I'll zoom in for this just a little bit more. With tri-state multiplexing, each pin can have 3 states. This is why it's called tri-state. It's also called Charlieplexing, after a salesman who promoted it for one of the electronics manufacturing companies. But each pin can either be positive, negative, or floating. And to drive an individual LED, and I think they just drive one LED at a time, they just take one of the pins positive and one of them negative. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 possible combinations of bridging these pairs of pins, and each of those has 2 polarities, so you could potentially have inverse parallel LEDs, so the 15 times those 2 LEDs gives 30 LED driving capability. To work out how many you can drive from a given number of pins, you multiply a number of pins times the number of pins minus 1. So in this case, there are 6 pins, 6 times 5 gives a total of 30 LEDs. If they'd used 5 pins, it would have been 5 times 4. That would only have driven 20 LEDs and not been enough for the display down here. So as an example of this, supposing we took C positive and D negative, the LEDs bridging those 2 pins are these ones here. And because the C was positive and the D was negative, the current would flow through this LED and that LED would light. If you swap the polarity, that LED would light. And by scanning through all the LEDs individually, they can basically just control the whole display. But it does give that strange swirly, shimmery effect when viewed in the camera, as opposed to different, the other multiplexing methods. Now, it's worth mentioning that when I bought this one, I also bought another one. And given it's missing this capacitor here, which I would have thought they'd add, but having said that, they are feeding it with an AC signal source, which is quite odd. So a lot of averaging is getting done inside the chip. This module is simpler than this one, which does have a capacitor, a ceramic capacitor, possibly for filtering, plus a diode. And it's also potentially got another capacitor across the supply rail for taking out those spikes that might occur. With capacitive droppers, if you get a voltage spike, the capacitor just tends to act like a filter and just basically pass it through. And it can actually damage circuitry if that finds its way to the chip. This is why the cheap Chinese Paduk microcontrollers actually say in their data sheet it's not suitable for use with capacitive droppers. They're basically covering themselves there. And I blew up a PIC microcontroller in my early days, an expensive ultraviolet erasable one with a capacitive dropper. So it's real, it's a thing. But there we have it. It's useful, it's calibratable, it does the job. It gives you a good indication of the voltage. So in that sense, it's quite a cheap meter, does the job. It's okay, it's an alright little thing.